And through a from his smile, my will, I slice through the light. Life wells you like the electric flame. Hold all everything else. Hold all rise against the years and years and years. Okay, let's go ahead and get this started. Y'all, let me make sure. That side of the board. All right. All right, so we're back. So this is for differential equations. Um, we just finished off first order equations, kind of with that last lecture. So what we want to start looking at this week, and what we'll kind of finish out this week, is basically, well, actually, we won't completely finish out this week, but what we're going to focus on this week is second order higher equations and how we go about solving those, kind of the types of those equations we can solve. And so we're going to get through basically through this week, we're going to get through all the main methods. There is going to be a couple sections from, so this is chapter 4, and there's going to be a couple sections for chapter 4 that I'm actually going to push back to after the midterm. And you'll kind of see why, but in some sense they have a lot to do with the things that'll come later in the course. And so I actually wanted to give you guys a second after the midterm to really absorb those sections so that you can then relate it to what we see sort of the last 2 weeks of the course. That also means again, so we'll get through this week. We'll get through most of chapter 4 and kind of everything we need for solving kind of second or higher order differential equations. And then we're going to take a midterm next week. So towards the end of the week, I'll message you guys with just the time slots for that. So again, you guys know both from the intro message and also from the orientation module that the tests are done over Zoom live. So I will be messaging y'all with which one of those time slots next Thursday, what time slot next Thursday would be best for you to come in. Etc. But that'll be next week. So we'll kind of get through the homework this week, and then next week, actually, I'll have a video up for you guys as a review for the midterm. So there'll be a review for the midterm, which I've got to rewrite for you guys because we're doing this in 5 weeks. I'm basically including more on this midterm than I would normally. So normally I have a first test, a second test, and then a final for this class. But because of the 5 weeks, there was no way to make that time spacing work. You guys would have been doing a crap load of homework that last week while trying to prepare for a final, which doesn't make any sense. So because of that, I mean, you'll see. So you'll see right now, actually, I don't have this stuff up for next week only because I need to rewrite the review, rewrite the test a little. So just give me some time towards the end of this week and I'll get that up for you guys and I'll send out a message. But next week, what you'll see is you'll see a review. You'll see a page with a review, a lecture on it as well, going over that review, and you'll have a couple days to look at that before we get in on the test. So good. But like I said, we did as much as we could do with first order differential equations. Let's look at some second order differential equations. And what we're going to look at today is second order or higher. So or higher. We'll look at actually pretty much this whole week. Second order, well, okay, what we're gonna look at today is second order or higher, or second or higher order. The key here is linear, homogeneous. Yes. Differential equations. We'll just abbreviate this at this point. That's the key. So again, remember what linear means. So linear here means the same thing we saw in the first chapter. Linear means that your coefficients are basically not a function of y. yeah, pretty much that they're not a function of y. And um, we'll talk about what homogeneous means here. Actually, I want to see if, give me a second. Let's see if linear shouldn't mean anything different here, but let me just make sure. Let's see. I wasn't misleading. All right. Um, So we're gonna look at linear, so the homogeneous, so I remember on that last lecture, if you remember, I was saying that they had a definition for homogeneous in section 2.5 that I didn't really want to talk about or give much to you guys because it was actually wouldn't jive with the definition we see here. So here, we're gonna use a definition for homogeneous, and this is what I want you to focus on, not just for this section, but really for this class. What we mean by homogeneous is basically the differential equation equals zero. So if the differential equation either already equals zero or you can rearrange it so it equals zero, then what do you call it? Then that's what we call a homogeneous differential equation. The other thing about the equations today, so it's linear homogeneous, second order or higher, linear homogeneous equations. We're going to look at constant coefficients. So the coefficients, so specifically these coefficients that are going to be in front of our derivatives of y, we're actually going to narrow them down to just specifically constants today. So a good example of this, I'm going to pull up one of the exercises. We'll get going. A good example of this type of equation is, this is number 3 in your exercises for this section. Again, so this is section 4.3. Y prime, or Y double prime, sorry. Minus Y prime minus 6y equals 0. So here's, I sort of gave you a lot of words here in this description. Here's practically what I mean. So again, first, linear, because coefficients in front of here are all either constant. Well, in this case, they're going to be constants, but in general, that means they're functions of x, functions of y. But second order. So notice the big difference, honestly, if you took this equation and took this part off, you already know how to solve something like this. So this could be a separable equation. It could be, you could solve it using an integrating factor. We already know how to solve this. So the big difference, not only today, but this week, is I'm adding on a higher derivative. What this says is the second derivative of y minus the first derivative of y minus 6 times y equals 0. So like I said, the homogeneous, so it equals 0 as to what tells you it's homogeneous. So this is the type of thing that we're going to focus on today. So the interesting thing then is, yeah, so if I introduce a second derivative, keep my coefficients constant, but if I introduce a second derivative, does this change much, kind of how we go about solving this? And the surprising thing is it does. It changes it actually a good bit. So you'll kind of see this as we go through this course. The one thing that I still think is crazy interesting about differential equations, and I thought the same when I first took this class in college, was that a lot of other math classes you've been in, like in the calculus sequence, it's like you start with some overarching ideas and techniques, and those techniques become sort of your cornerstone for how you solve a ton of different equations, right? Or a ton of different problems. So in Cal 1, you started with derivatives and you could do a ton of different derivatives with them, right? In Cal 2, you started with the integral and then you figured out how to do a ton of different integrals and you really didn't actually have many methods, right? So in Cal 2, there wasn't actually a ton of methods overall and it gave you a ton of problems. And in Cal 1, there wasn't a ton of methods and it gave you a ton of problems. But what we've already seen in this class, as far as differential equations, so we haven't seen the same thing. You could think back to what we did the first week. We had one method for these differential equations that we could separate, and then the ones that we couldn't, suddenly we needed a whole different method. We introduced the idea of an integrating factor. And then we went to, we went to exact equations, right? So then if we couldn't even do what do you call it, an integrating factor, then we had a whole different method that really had a different, I mean, uh, had some similar ideas behind it, but it really had a different idea behind it, right? And then 2.5 was even worse because then it was like, here's these corner problems that neither of any of our methods solve, and here's a completely different method to get through those, right? And now we go to second order differential equations. We introduce a second derivative at the least to this problem, and I'm saying, yeah, unfortunately, there's a whole different method here. Right, so the commonalities in all these is just your knowledge of how to take derivatives and integrals, but the methods for all these, there's just a wild, a bunch of different methods for them. And they only cover, I mean, some of them cover a lot of problems, but they only cover certain types of problems, right? So this is very common for differential equations. We don't have some, the differential equations is kind of interesting because basically what we're saying is like these things are complex enough that we don't have some governing principle or idea that we can develop and apply, and then it just sort of cascades and solves a bunch of different problems, right? That doesn't exist. We are past that point in mathematics, unfortunately. That's actually some of the research that I'm doing and the papers I'm trying to write right now. I'm trying to actually work towards some more general methods on solving what's called partial differential equations. We talked about partial differential equations a little bit last week when we did exact equations, but so I'm trying to work to some of those methods myself. And then anybody who's studying, differential equations or partial differential equations, doing research in them, that's ultimately a bit their holy grail, right? Because this is still a part of mathematics where we don't have great ideas and methodologies that apply to a bunch of differential equations. We just have certain types of equations that have this method and certain types of equations that have this method, and none the twain mate, right? So there's no overarching great theory or idea that even sticks those together or covers those. So that is what you're going to see in differential equations. Hopefully, if I get time to keep working on these papers, maybe I'll come up with a method that does cover a lot of these varieties of equations. Anyways, so at least second derivative, at least second order or higher, constant coefficients equals 0, homogeneous. That's what we're going to look at today. So, like I said, unfortunately, there is, once we get to a second derivative, we need whole new methods to get at this. And what I want to show you today is the method for this is kind of interesting because in some sense, again, because we have no overarching ideas or concepts that really apply to a ton of differential equations, each time we're kind of stuck in some sense doing a little trial and error and guessing at a method that could work, right? And I think this method that we're going to look at is kind of the epitome of that, of trial and error, of guessing at something that'll work. So take a look at kind of now not just the structure, but what this differential equation says. So this differential equation says there is some function that when I take its second derivative, subtract the first derivative, then subtract 6 times that y, here's the kicker, I get 0. So there's some function that when I do these derivatives, somehow these derivatives work out well enough that they sort of cancel each other out, right? Or they kind of cover each other in some way. But a better way to think about it, they cancel each other out. So we're going to do a little trial and error. We're going to do a little guess. Thing that we have to guess is what type of function can we think of? So now that you've done Cal 1 and Cal 2, and you have a very good idea of how derivatives of a bunch of different types of functions work, and then integrals kind of working of all those types of functions working them backwards. So we want to specifically think of derivatives What type of function can you think of where its derivatives would tend to cancel each other out? Give you guys, I'm just gonna pace back and forth. I'll give you guys this second to kind of think about that a little. What do you guys think? And just what I want to do is just remind us of, let's say we are doing something. So let's look at some power functions or really polynomials. But if you look at some power functions, right, and I take derivatives of them. So let's say, very simple, let's say I'm doing something like x cubed and I take a derivative. What does that give me? That's going to give me 3x squared. Would a 3x squared cancel an x cubed out? Yeah. So it is not likely that the solution to this differential equation, the solution to y, is some sort of power function like x cubed. Because the problem is, once I start taking the derivatives, I end up with unlike terms. I end up with powers that are not going to cancel with each other, like when we're adding or subtracting. And that's again specifically because of the structure here. That is because we are subtracting and adding our y double primes, our second derivatives, first derivatives, and y's. If this had some other structure, then maybe this comes into play. But definitely here, I need adding and subtracting to cancel things out, and that's not going to happen here. And if you think about some others, so that's what you want to do is you want to kind of surf through your mind on these types of functions that we've looked at in the calculus sequence and think about derivatives and just kind of check, do these things tend to cancel each other out? Take the derivative of sine of x, what do you get? That you get a cosine x. Does a cosine and sine cancel each other out? No, unfortunately not. So that's what you kind of want to do. You want to think about log functions, exponential functions, all these types of functions that you saw, square roots, rational functions. So of all those variety of functions that you saw in Cal 1, thinking about their derivatives, what type of function tends to cancel itself out after derivatives? So I think you guys got it. So again, notice that with power functions, we get a power function out of it, but we get something different that's not a like term. With trig functions, the same. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of secant square or tangent is secant square, right? You constantly get different functions. There's only one function, actually, one type of function where when you take its derivative, or its integral for that matter, but when you take its derivative, you get the same function back. That's an exponential function. So if you think about exponential functions, something like, I don't know, e to the 2x, whatever. When you take the derivative of that, what is the derivative of that? That's 2e to the 2x, right? But notice then if I tried to add or subtract these together, I can actually do that. I can add or subtract the first derivative with the original because they are like terms. So this is a function that if I take derivatives of it, I start putting coefficients in front of the results, I could possibly add or subtract these in a way where everything cancels out and I get 0. And again, that's the way I'm reading these equations, because it's a homogeneous equation, because it's linear with constant coefficients. That's kind of what I'm looking for. I'm looking for a function that after derivatives, coefficients multiplied, I have like terms so that when they add together, subtract, whatever, when you kind of roll them all together, possibly get them to cancel out, get 0, right? You need the like terms. So it looks like exponential functions are actually our only function that is kind of a possible solution to something like this. It's the only one that's going to behave the way we want. After derivatives, I get the same function, be a different coefficient. So then when I add and subtract them together, I can adjust the coefficients and maybe make that happen, make it equal to 0. So like I said, trial and error. We just know from our knowledge of derivatives that in a sense, these are the only types of functions that could be solutions to a linear homogeneous differential equation with constant coefficients. And so what we're gonna do is we're gonna make a guess. We're basically gonna make a generic guess at the solution. We know that it has to be an e to the x, basically. So here's how we play this game. We suppose, or we suggest, y equals e to the mx. So basically, we know it has to be an e to the x function. Really, the only thing we don't know is what constant I have in front of x. But we guess that the solution is this. And if we think the solution is this, what we can do then is we can figure out what y prime is and what y double prime is, and then plug them in and essentially solve for m. Yeah, and this is kind of a clever method because, like I said, it's trial and error. There's nothing mathematically revelatory or great about this method. All we're saying is from my knowledge of Cal 1, thinking through derivatives, this is the only type of function that could be a solution to this. You would have like terms that cancel out. So I'm gonna guess it's that type of function. And now I'm gonna use what I know from calculus and algebra to go and basically fill in the blank there, figure out what m is. So let's do this. So I'm gonna suppose that it's this. And if it's this, what we can figure out from there is what y prime is, and we can figure out what y double prime is. Actually, I would like you guys to do that. So I'll pause on your side. I'll pause on my side. Go ahead. If this is what y equals, this is my thought about what y should be. Go ahead and figure out what y prime, the first derivative, and y double prime, the second derivative is. So go ahead and work on that for a second. All right, let's see what you got. So when you take the first derivative here, what would the first derivative be? Yeah, now hopefully you're well used to this. So you multiply by m. This is essentially using the chain rule. It's really almost don't need to see it as the chain rule, or at least maybe you don't need to see it there that way. I mean, it's simply just multiply by your coefficient. The first derivative is m e to the mx. Now the fun part is then, at least I think the fun revelatory part here is then what's the second derivative? So I'm going to take this, take the derivative of that, and to do that, I'm again going to drop down and multiply by m. This is just a coefficient, so it comes along for the ride. We end up with m squared e to the mx. So that would be y prime, that would be y double. So that's calculus. You guys know how to do that. Now what I have is I have a representation of y prime, and y double prime. I can plug those in, and now we can play algebra. So that's what we're going to do. I'm going to rewrite this with just everything plugged in. So what we have is m squared e to the mx. Yes. M e to the mx. Then minus 6 e to the mx. Okay, give me a second here. Thank you. Right, so we end up with something like this. And all of this, by the way, so plugging in all this equals 0. Now what we're gonna do is we're gonna do some algebra, because at least even if I don't know, so even if you don't know where you're going with this, or you're not sure where I'm going with this, I see an equation here and I want to try to solve for, so basically we want to try to solve for m. I also see a bunch of like terms here. So notice that every one of these involves e to the mx. So at the least, if I knew nothing about where I was going, and if you knew nothing about where I was going, or you had no idea what you could do with this, let's just factor out some common factors, because that's a cool algebra thing that's there and we can do it. So we factor out e to the mx. What does that leave us with? That leaves us with m squared minus m minus 6. Notice really quick how suspiciously similar this is to sort of the form of our original differential equation, right? Even that original differential equation, you may have looked at that and said, well, that looks a hell of a lot like a quadratic equation, right? And it's not a quadratic equation because it's not powers of a function, but in some sense, it's sort of some sort of derivative, some sort of similar idea or similar type of equation in terms of derivatives rather than powers, right? Now, once you plug this in, you really do get a quadratic equation. So we have e to the mx times m squared minus m minus 6 equals 0. Again, my ultimate goal is I want to figure out what m is. I now know that thing A times thing B equals 0. So we know that either e to the mx equals 0 or this equals 0. I want you to think really quick. Let's think about e to the mx equals 0. Does e to the mx ever equal 0? Think about I guess it would be the range of a exponential function. In fact, it's never going to equal 0. No matter what power you raise e to, not just e, but any base, it never equals 0. So again, what I'm trying to do is solve for m here, because again, I suppose that y is equal to e to the mx, so I just want to figure out what that m is. I can't get it from this factor, because e to the mx never equals 0. But I could get it from here. So if e to the mx never equals 0, the only way that this equation equals 0 is if m squared minus m minus 6 equals 0. So this is the thing that I'm really solving, or I need to solve in order to figure out m. And you may already be playing forward in your mind, or just some of the consequences of this and how this is going to work out. So if m squared minus m minus 6 equals 0, how many solutions am I likely going to end up with on this? Probably 2 solutions. So there's actually going to be 2 possibilities for my solution. We'll talk about how we kind of deal with that. But you need to solve this. That's easy enough to solve. I still will give you guys a second to do that. So pause on your side, I'll pause on my side. Go ahead and solve that quadratic equation there really quick. All right, see what you get. This is easy. This is really honestly easy peasy algebra. This isn't easy. So but for the sake of showing it, at least for a second, what this is going to be, m minus 3 times m plus 2. Set each of those equal to 0. So we get 2 possibilities here, m equals 3 or m equals negative 2. So what we're saying is basically, what we're saying now is if I'm looking for the solution to this, I now know that either e to the 3x or e to the negative 2x are solutions to this differential equation. So each of those individually, you plug them in here. Take the second derivative and the first derivative of each of those, plug them in individually. This is going to add up to 0. So we have our solution. What this tells me is there are, well, not write the full solution out yet, but there are 2 possible solutions. E to the 3x and e to the negative 2x. So then my question to you is, first of all, what if I multiplied one of those by a coefficient? So I guess, sorry. This gives you y equals e to the 3x. This gives you y equals e to the negative 2x. So what I'm saying is each of these then are solutions to this differential equation. Now I want to check a couple things. So this will definitely work. What if I made another solution? What if I made, if I did maybe something like 4 times e to the 3x? Would that also be a solution to this equation? But when I assumed this solution, I basically, one of the things to notice is I missed assuming that there was a coefficient there. That I have a coefficient in front. So, and maybe you don't have a thought on that. Maybe the idea is clear to you. Maybe you have an inkling of an idea and it's not sure. But if you think about it, when I take derivatives of something like this, um, with um, with the coefficients, I just want to. So you guys, I missed something in the explanation here, or at least instead of doing it this way. So I was gonna ask you about this coefficient, but I think a better way to talk about this is we should have assumed there was a coefficient to begin with. So let's assume that our initial solution, or our not even our initial, our guess at our solution is c times e to the mx. So it's some coefficient times e to the mx. So let me repair my mistake here. I'm gonna work out the first derivative and the second derivative with that c added. So with the c added, when I do the first derivative, this is gonna be mc e to the mx. And when I do the second derivative, then it's gonna be m squared c to the c e to the mx. So it doesn't really change it that much, but you are possibly multiplying by a coefficient. So I guess back to the question I sort of asked you guys, if I added a 4 into this e to the 3x, what it would change is then every derivative would basically have a 4. So we know that when we take derivatives, the constants follow. So every derivative have an extra 4 multiplied in it. But if you think about that, that's not going to change whether or e to the 3x is a solution of this. It's not gonna change this equation equaling 0, because all I'm doing is adding that same coefficient to each piece here, which means I can factor it out and I'm still gonna get, I'm still gonna get 0. So let me show you that algebraically. So these are now my y prime, etc., my y double prime. So we will have squared. I'm actually going to put the c outside. The c m squared e to the 3x minus c m e to the mx. That's, um, 6c e to the mx. And so then when we factor out a common factor, common factor is no longer e to the mx, it's e to the mx times c. But still, c times e to the mx can't equal 0, assuming c isn't 0. So we'll always assume that our coefficient isn't 0. It still means m squared minus m minus 6 equals 0. So we still end up with the same solutions here. The difference is, for each of these, there's possibly some coefficient in front of i.e. e to the space 3x and e to the negative 2x. And when I made this assumed solution, I intentionally left c vague, right? It's a constant, but I don't know what it is. That means for the first solution, there's possibly one constant. We'll mark that C1. And for the second solution, there's possibly a different constant. Now they could be the same as each other, but they just don't have to be. So again, we have two possible solutions. The only difference here is now there's possibly a coefficient in front of each of those solutions. So then, my next question is, what if I added these two solutions together? So we know that, for instance, if you plug in this, so these are now solutions to my differential equation, which means when I plug in this and I do all the work on the left, I get 0. If I plug in this and I do all the work on the left, I get 0. But what about if I added those two together? C1 e to the 3x plus C2 e to the negative 2x. So what if I made a solution out of by adding those two possibilities together? Would this also be a solution to this differential equation? What do you guys think? And hopefully this kind of, what do you call it? You're leaning towards yes on this, or at least this makes sense. So if you think about it, again, if you think about what we know about derivatives, so not how to find a derivative, but the patterns with derivatives, we know that if I add two functions together, if I have two functions added together and I want to find the derivative, I can just find the derivative of each separately. Adding or subtracting, then we deal with each of them separately when I'm doing the derivative. So if you think about this now general, so we're going to call this, I'm going to call this a, of a general solution. I think they use YC in the book. Let me see if, or is it YG? They just don't use either of that in this section, but that's okay. So I guess we don't have to. So if I make this sort of, get, again, a super general solution of adding the two possibilities that we got together. If I plug this into the differential equation, the thing is I don't even have to work the pieces out. We know that y double prime minus y prime minus 6y of the first part is 0. Know that y double prime minus y prime minus 6y of the second part is 0. So because of the way derivatives work, the plugging this into here is going to give me 0 plus 0, which equals 0, which is what I want it to equal for the differential equation. So sorry, that was bad, probably badly explained, but also just a lot of words at once, and I was trying to push across the concept. So what I'm saying here is each of these individually, yes, those are solutions. We worked the algebra out, we figured out what we needed to plug in for M. But if you add the two solutions together, this is also a solution. Because when I do all of the derivative work here, multiplying by a constant coefficient, I know that this part goes to 0 and this part goes to 0. Differential equation. Therefore, both of them added together also goes to 0, because 0 plus 0 is 0. So when you're solving these, you're going to get these sort of separate solutions, these separate possible solutions. Your general solution is actually those two pieces added together. You can always add them together, and your derivatives are just going to work on each one separately. And so that means we're still going to get 0. This one gives me 0, this one gives me 0 through this differential equation. So the sum of those also gives me 0. So our general solution then to this differential equation, this linear homogeneous differential equation, is this. It is the two parts that you get, or the parts that you get bind together to make one general solution. Now this general solution, notice that this general solution, it has these coefficients that we don't know what they are. So that's what makes it sort of, when I say general, what I mean is basically literally any real number can be plugged into these. So any constant coefficient combination of e to the 3x and e to the negative 2x is actually a solution to this differential equation. So there's not just one solution to this differential equation, there's a whole ton, there's a crap load of them. They call it a family of solutions. And you can make any of those solutions, any of those family, any solution in this family by just plugging a different number for C1 and C2. So this is how we solve this second order linear homogeneous differential equation. And honestly, this whole section is exactly these problems. So in this whole section where it's always going to be a linear differential equation because coefficients don't involve y. It's going to be homogeneous because it equals 0, and it's going to be constant coefficients. So the kind of drum roll bum of this section is pretty much do every single time you do the same thing. You suppose your general solution is c e to the mx, because that is the only type of equation. When I take derivatives, it returns the same thing. So we'll have like terms that combine to 0. So you suppose it's this, you form your derivatives and you plug them in, and we're always going to end up with, it won't always be a quadratic, but we're always going to end up with some polynomial here that we can solve. So let's look at a couple more examples. We won't have to look at a lot of them. So this lecture should be shorter. The earlier lecture that I did today for another class, I told them it was going to be shorter, and then it still ended up being maybe not as long, but it still ended up being longer than I thought. So this lecture should be shorter than a lot of our other lectures, because this is actually all we're going to do every time. So I want to show you guys a couple more, just with some basically I want to show you a couple more with some special circumstances that come up, but also just show you a couple more so you can practice. All right, so that was 3. Let's look at 5. 5 is y double prime plus 8y prime plus 16y equals 0. And again, what I'm going to do is I'm going to start by assuming that my solution is c e to the mx. Then I'm going to figure out first derivative, second derivative, plug them in, and then solve. So you get an equation where you're trying to figure out what makes it equal to 0. You work from there. So what I'd like you guys to do is basically get as far as you can on that. So don't think you have to get all the way to a solution, but I want you to at least get to the part where you solve for the equals 0. Then we'll talk about that, putting the solution together from there and kind of what that means from there. But I'll have you guys do that. So again, you have this one example. It's pretty, pretty easy to see where to go from there. So go ahead and pause on your side. I'll pause on my side. Start working derivatives and work this through. All right, let's see where you guys got on this. The y prime here should be then cm the mx. Y double prime should be then cm squared e to the mx. Hopefully you saw too when you did that kind of was like, oh, okay. Like again, if I make the same assumption to begin with for y, then every time y prime and y double prime are going to kind of be literally the exact same results there. So then what I want to do is I want to plug this in. So we end up with c m squared e to the mx plus 8c e to the mx plus 16 c e to the mx. All of that equals 0. So now I need to solve this equation. I can start by factoring out a common factor. It's gonna be C e to the mx. That'll leave me with m squared plus 8 plus 16 in parentheses. And I need to go set these equal to 0 and solve. So just like we saw the last time, e to the mx, general exponential function never equals 0. For any power you put in there, um, you're getting something above 0. So the only way this works is if c equals 0, but c, basically, we're never going to consider c equals 0 because in some sense it's a trivial solution. So if c equals 0, then this is not an e to the mx, it's just y equals 0. And if you think about it, y equals 0, of course y equals 0 works. So 0, 0, 0 would make this automatically 0. So we call that kind of a trivial solution. It's like, obviously it works, but there are other solutions, and really the main solutions that we're looking for, right? So we're assuming c is not equal to 0. And if it isn't, then this never equals 0. So this cannot equal 0. Which means this is the part that I need to solve. Sorry, this is 8m. Figure out how it equals 0. And I think this is finally going. So factoring this, you're going to end up with m plus 4 equals 0, m plus 4 squared equals 0. And so actually then we get kind of one solution here, m equals -4. But I will say, notice that, so we get one solution, and we know for quadratic equations that's one of our possibilities, but the what's the word for that they use in college algebra? The multiplicity of that solution is 2. And so specifically when you have basically a double solution like this, like on the previous one, we got 2 solutions, we wrote out each of them. But when you have a double solution like this, because this is a 5-week class, I didn't want to go through kind of the math behind this, but you can look at this in section 4.2 if you need something to sort of justify it for you. But if you end up with a double solution like this, or in this case, in terms of quadratic equations, just one solution that happens twice because your factor is squared, then definitely one of our possible solutions is e to the -4x. But it ends up, specifically when you have a double solution like that, there is a second possible solution. Second possible solution, so again, it's going to be a different coefficient possibly. But the kicker here is basically x e to the -4x also possibly, not only possibly, also works as a solution for this equation. And actually, let me check one thing to make sure I wrote that the right way. Make sure it's general. Um, So it ends up, surprisingly, that sticking an x in front of basically our previous solution, if you run that through this differential equation, it also works. In fact, maybe again, so I can't do the math theory to prove it for you, but actually we can still just plug it in, kind of trial and error, but we can plug it in and work it out and just see if it works. Actually no. So ideally, yes, again, that's what I'd like to do, is I just have you guys plug this in, find the first derivative of this and second derivative, and you'll see that this actually, plugging it in, you'll see that it equals 0. However, that's going to be a bunch of product rule anyway, so it's just going to take some time to do that. So I'll ask you guys right now to trust me. Your own time, though, like, that's honestly a good exercise. So you do need to kind of prove to your mind, at least get the connection in your mind that this does work. So it's honestly a good exercise. So if you get some extra time, go back this lecture, pause it and go back and actually find the first and second derivative of this, which is going to involve the product rule, and then go plug them in and just kind of check that that works. but it does work. We end up with these two possible solutions. If these are two possible solutions, how would I write the general solution? Just stick them together with a plus sign. My general solution then is C1 e to the negative 4x plus C2 e to the x e to the negative 4x. That would be the general solution to the differential equation. I want you to, again, we'll try to get an Oprah moment going, a kind of connecting moment, an aha moment. If you go back to this first equation we solved, ended up with a quadratic equation, is that equal to 0? You end up with a quadratic equation where when you solve this, you get two distinct solutions. And if you think back to solving quadratic equations, basically there was three possibilities when you solve the quadratic equation: either two distinct solutions, or one solution, kind of twice, right? So if you notice, what's happening here is essentially the types of solutions you're going to see to these linear homogeneous differential equations, in this right now of second order constant coefficients, is they're separated, the types of solutions you're going to get basically are separated out by or mimic, they're separated out by sorry, just they follow the pattern of the types of solutions that you get to quadratic equations. You either get two distinct solutions, so you'll have two pieces that sort of look like this, or you get one repeated solution. And if you get one repeated solution, we're basically our second solution to the differential equation is just the same thing with an x stuck in front of it. So then we can start predicting what this third possibility is. Because again, with quadratic equations, there was just three possibilities: two distinct solutions, one solution. What was the third possibility? Third possibility was that solutions were complex numbers, actually complex conjugates of each other. There was two of them. Third possibility was basically no solutions, but you learned somewhere in algebra that no solutions actually meant the solutions were complex numbers. Two distinct solutions, one solution, two distinct real solutions, one solution, one real solution, or zero real solutions, which means two complex numbers as solutions. So those are the same possibilities that are going to pop out here. Two distinct solutions, one solution. That gets our set. So that gives us our little special second part here. Or this next example then is going to be no real numbers as solutions, so two complex numbers as solutions. So let's look at an example that plays out that way. Look at something like this. This will be 13. And I'll also, let me write it and then I'll turn the camera so you guys can see it. 3y double prime plus 2y prime plus y 0. We're gonna play the same game through though. So we start with y equals c e to the mx. This time again, since you guys especially now know that every time you take the first and second derivative with that as your assumed solution, we're gonna get the same results. So y prime is cm e to the mx. Y double prime is the m squared e to the mx. And then I'm gonna go plug these in. We end up with 3c m squared e to the mx plus 2cm e to the mx plus d e to the mx equals 0. And we're gonna factor out our common factor. So notice each time we really get down to the same, like, so we're gonna factor out a common factor and we end up with that parentheses left over that's just, in this case, again, because this is second order, we always end up with a quadratic equation there. So that quadratic equation, by the way, that you get, so they, in this section, they call that the auxiliary equation. And if you want, if you kind of see that result before you even get there, so I kind of noted on the first one how similar the m squared minus m minus 6, that parenthesis was to the original. So basically that auxiliary equation basically looks exactly like the original equation, just instead of derivatives, you're doing powers. So instead of derivatives of y, it's power functions. If you see that similarity and you want to just write it, you basically just want to fast forward through the problem and write it, set it equal to 0 and solve. So again, it's just basically is if your mind sees that pattern and you want to fast forward through the problem and write that and just solve it from there, go ahead. So as long as you see the pattern and it's efficient for you and you're not going to miss anything, do that. You don't have to write all this stuff. But to be a little complete about this, just when I'm presenting it for y'all. So I'm gonna factor out ce to the mx, and that's gonna leave me with 3m squared plus 2m plus 1. That's my auxiliary equation. I know that this never equals 0. This is the only thing that can equal 0. Set that equal to 0 and solve. 3m squared plus 2m plus 1 equals 0. And then we want to solve for m. So this is where, again, I want you to take what you know. I mean, this is just college algebra. I want you to go ahead and solve this. And then let's see what we get and then see how we kind of play with that. So pause on your side, I'll pause on my side. Let's see what we get. All right, so let's see what you guys are getting. And I'm realizing too, so just as a note, so we'll do this problem and it is getting really late on this side, so I'm gonna have to do a second part to this lecture, which is fine, because there's probably two more. There's at least, well, yeah, there's at least two more examples we need to look at after this. But solving this, hopefully, so maybe you tried to factor this, and hopefully in factoring this, you realize this actually can't be factored. So then our only way of solving this actually would be the quadratic form. Have to do negative b plus or minus the square root of, so it's going to be -2 plus or minus the square root of 2 squared minus 4 times 3 times 1 all divided by 2 times 1. So in working that through, what you should start to, or should have found, what you should start to find, so this would be -2 plus or minus, this is 4 minus 12 basically, so the square root of -8. Square root of -8 is going to be, so simplifying, that's going to be 2 square roots of 2i. -2 plus or minus 2 square roots of 2i. which means that 2 on the bottom is gonna divide into each of these pieces, so we at least don't get a fraction, which is nice. We get kind of a clean, this is gonna be -1 plus or minus square root of 2i. But main thing there is that we get, like I was predicting and like we were talking about, you get complex numbers as solutions. Now, in a previous class, you get complex numbers. That means there isn't a solution, because usually when we're solving for zero, we're looking for x-intercepts, or maybe in a calculus class, you're looking for an x value where there's an inflection point, right? Or there's a what do you call it, a high or low in the graph, a relative minimum or maximum, right? So you're looking for an actual point on the graph, and points on the graph have to correspond to real numbers. The interesting thing here, though, so again, we would get this and we would just throw it away, and we'd say, no deal, no dice. That doesn't give us anything. But um, let's talk about kind of what this looks like then. So what I'm saying is then there are two possible solutions. So now I guess part of the first thing I want to say is, again, here we're not looking for points on a graph, we're looking for functions. We're looking for functional solutions, or functions as solutions to this differential equation. So I couldn't mark this point on a graph, but I sure enough could write something like this. I could write C1e to the -1 plus square root of 2i. And I can also write C2 e to the -1 minus the square root of 2i. So there's nothing that says that those can't be powers of e. Although it still may look weird. So how in the world am I going to raise e now to not even just some funky exponent like square root of 2, but something involving I, right? So the interesting thing is that, and you probably saw this mentioned a little bit in either the Cal 1 or Cal 2 class, or maybe both. There is something called Euler's equation that actually freakily relates a natural number, pi, and the imaginary number, square root of -1, or I. It relates them all to each other. This was something discovered by a mathematician named Euler. And when I say freaky, at least I'll write it. If you've never seen it before, hopefully this stays freaky for you. Because if you think about what you've learned in mathematics, somewhere, some way before geometry class in high school, they introduced you to the idea of pi, this irrational number that never ends and never repeats. But somehow, when you take the circumference of a circle and divide by the diameter, you always get that single number, right? And then somewhere you are introduced to the imaginary number. Suddenly, we shouldn't be able to take the square root of -1, but we can, and it shows up in the equations for how electronics work, etc. It shows up in the real world. There are equations that we solve for things that really work, whose only solutions are I. But that's not even, I don't even know how to represent that number, right? It's not even a decimal, it's not any of that. And then, um, again, then there's e, this natural number e, which originally may have been presented to you as maybe a sort of a version of the golden ratio, right? And then your teacher may have remarked how things that grow in nature grow according to this spiral pattern, roughly, actually not just roughly, but pretty close to the spiral pattern governed by E. In fact, governed actually by E raised to a power. So there's this weird number E that pops up when we look at the natural world and the growth of things. There's this weird number I that pops up when we look at electromagnetism and a bunch of things in the universe that sort of again exist, but I can't codify this number as a real number. And there's this funky number pi that pops up in circles and all these other weird places where yeah, just so there's these three numbers that pop up weirdly in a ton of places in the universe. And Euler basically figured out a way to relate, or figured out that these three numbers are actually related to each other, even though none of their contexts suggest that they should be related to each other. none of the numbers suggest they should be related to each other, right? I mean, there are three different numbers, weird numbers that pop up everywhere, but they talk about different things. However, I'm gonna get this equation for you guys. There's a couple different ways to write this, but basically Euler's formula, what he found is that if you take E, you raise it to the, well, actually, I'm sorry, I was talking about pi, I guess, well, pi doesn't come into this, but it does, it sort of does come into it because we're talking about angles, but e to the I theta. So if you raise e to an angle, probably in radians, multiplied by the imaginary number, this can be rewritten or re-represented as cosine of theta plus I times sine of theta. Debate whether I'm going to show you all the mathematics behind this or whether we'll just. Probably won't show you all the mathematics behind it, but I'll at least suggest some of it so you guys can follow along and just sort of connects and makes sense, but good. So we get this nice thing called Euler's equation. So Euler's equation is going to help us deal with this because, or at least algebraically deal with this a little bit because, again, what in the world does this mean? Well, one of the things that you can look at here, um, what this means, so first of all, what this means, mirroring the previous problems, is that my solution is C1 e to the -1 plus the square root of 2 of I plus C2 e to the -1 minus the square root of 2i. Now, what I'd like you to notice is that both of these e parts, and there's just a lot of things similar there, but in particular, this e to the -1 matches on both of those. And also, I want you to remember some of your patterns of exponents. So if I have e raised to a power that is the sum of two exponents, I could rewrite that as e to the first part times e to the second part. Because again, with exponents, when you multiply, you really add the exponents. So what I'm saying is I could rewrite this as e -1. Right, and I'm sorry, when I wrote these, I should have put, this was mx, I should have put x's on all this. Sorry guys. So that should be an x, that should be an x. That's what I knew I was forgetting something. That should be an x, that should be an x. So what I'm gonna do here is I'm gonna kind of distribute the x through, but then I'm gonna write this, since it's the sum of two exponents, I'm gonna basically break it apart into e raised to a power times e raised to a power. So it's gonna be e raised to the -1x or negative x times e to the square root of 2i. The second one, I'm gonna do the same thing. I'm gonna distribute the x through, then separate the two powers of e there. So it's e to the -x again, times now e to the negative square root of 2i. Notice now that e to the -x is a common factor. So we can factor that out. So we get e to the negative x times c1 e to the square root of 2i plus c2 e to the negative square root of 2i. And what I want you to notice is that now each of these parts, the e to the square root of 2i and the e to the negative square root of 2i, they look like the front end of this Euler equation, which means we can replace each of those with the back end of this Euler equation. Basically, if you look at it, square root of 2 is your theta. And once you do that, you could do some algebra there with then, because then you're gonna have e raised again to powers that are added together. So there's a bunch of algebra to work from here that is all based on patterns of exponents. So what I'd like to do again, because we have a short class, I want to show you sort of the result of this, and then hopefully you can see there's a pattern basically for once you see what these solutions are, how you write this end solution. So let me do that. Always hard to summarize. Okay. Well, again, like I said, let me just summarize this because there is a bunch of algebra from here. So what this means, what you end up with this is this all then becomes, so it's e to the negative x. So basically, if you go back to what our original solution is, the number on the first part of your complex numbers was -1. So that's going to end up e to the negative x, or in front of x there. And then in parentheses, this, when you substitute these with this and start doing the work, what you end up with is c1 cosine of square root of 2x. Sorry. These also would have had x's, by the way. Missing a bunch of things. Sorry, that should have had an x, that should have had an x, that should have had an x, that should have had an x. So you end up with cosine of square root of 2x plus c2 sine square root of 2x. Although I think actually that one has an I on it. The algebra that gets worked out. Yeah. So a bunch of algebra to work out. Lots of like terms that are canceling, but you end up with this as a solution. So if your solutions are complex numbers like this, basically the first number there ends up here as your e to that number x. And the second number here ends up as your numbers in front of x here, and basically the inside of this is always the same form. C1 cosine of that number times x plus C2 sine of that same number times x. So if you get complex numbers as solutions, if there's no real solution, you're actually always going to end up with this form as a general solution. All right. Like I said, there's 2 more examples to work with, but I need to get some food for my son and just kind of get on with the rest of the night. So I will come back with a second part to this lecture. See you guys there.